Okay, looks like we're recording. That's good. Okay, so no one showed up. That's fine, because instead of, well, that's what that is. So we can just, I haven't finished the homework, as you can see, but just in case you don't believe that I'm capable, we can look at my homework grades. As you can see, I'm passing all of them. I haven't finished this one yet. I only got a year-end test, so I am capable of doing well in class, just in case you don't believe. So I'm not going to give away the answer. Well, I suppose I've given away number one, but oh well. I'm not going to do the entire homework until after the homework is due, because I'm pretty sure that that would be cheating, and I don't want to get burned. So instead, I'm just going to explain an important part of doing some of the problems. So I think first, how about I show you. Let's go to Paint. Let's show how to do number one. So as you can see, I actually got it wrong the first time, and that's just a small mistake. So make sure not to do that. Let's not do that again. But basically the way, because I can just show the entire problem because I've already done it. So we have C2H2. So it's hybridization. So because now the C atom needs 8 electrons in its valence shell, which would be sp3. But because carbon can make double bonds, because carbon can make double bonds or triple bonds with other carbons, we have to find what it looks like. That's just one. Hello. Do you have any specific questions? I was just going over number one.
Okay, no, I don't have any questions. I just want to listen and see what you're doing.
Okay. Yeah, I'm just explaining how to do number one really quickly because I already did it. So the answer's already there. I'm not going to give away, I'm going to try and not give away a bunch of questions, but I do want to explain how to do some of the problems. So like I was saying, because carbon can form double or triple bonds with other carbons, and there's 2 carbons in this molecule, we want to sketch it out to find out how many either electron pairs or sigma bonds there would be, which is a single bond, or the first bond if it's a double or triple bond, in order to find out what the hybridization would be, because pi bonds do not factor in the hybridization because they're pure p. So we have 1 bond there, 1 bond there, like this. And because this molecule has exactly 2 carbons, it's actually going to be the same for both carbons. So how many bonds should there be here? There has to be 1, but how many are there going to be? Well, in order to find that out, we can use NASU, NASU. So N is the total number of, if we add up all the electrons in the valence shells that will be required to fill them. So for 2 carbons and 2 hydrogens, each hydrogen is 2, so that's 4. And then each carbon is 8, so that's 16. So we get, was it 20? Yeah, I think it's 20. So that's our N, and our A would be carbon is 4. And so there's 2 carbons, that's 8. And there's 2 hydrogens, but they're both 1, so that's 10. So our N, you can go ahead and just, here, let me open up an Excel sheet just so I'm not just spitting numbers out. Nice and slow, like Excel, there we go. So we have our N, which is, what is it again? 2 carbons is 18, 16, plus 4 is 20, 20. And our A will be 10. And then our S is the number of shared, which shared is N minus A. So we get 10 shared. And then there's no free electrons. There's no free electron pairs because the A minus the S would equal the unshared. And there aren't any. There are no unshared electron pairs. That means that and if you remember, the number of bonds is half of the S. So the number of bonds would be 10 over 2, which is 5. So there's 5 bonds. So pretty easily you can see that because there's no electron pairs, all of the bonds. Oh, okay, that's weird. Anyway. Oh, what's my screen doing? My computer's throwing up a little bit. Okay, that was weird. Anyway, so there's 5 bonds. Oh, my computer screen. What is going on? I'm so confused. What are you? What's my computer doing? I think I have too much stuff open. It's throwing up. Okay, let's close Excel then. Yeah, we want our computer to work. Okay, I think I just have too many things open. Anything else I can close? I can just close some of this random stuff. Yeah. Let's hope that fixes it. Anyway, if I can continue without my computer breaking for some reason. So we have these 5 bonds. This one's pretty easy one. I just messed it up, but it's whatever. So 5 bonds, no unshared electrons. So because we have these two bonds here are pi bonds. Because they're pi bonds, so we have 2 of them, they do not factor into hybridization. However, we have 3 sigma bonds. Ooh, that's a terrible sigma, but that's because it's in paint. There we go. So we have 3 sigma bonds, but per carbon, we only have 2. That means that each carbon, so it's asking for C, so per carbon, it would be sp hybridized. So that's our answer. You can see I got that was, yeah, that's the answer. Number 2, actually, it looks a little bit, so it does look a little bit scary. I did want to show how to do it. So I think we'll open up, we'll just, yeah, see if I can just get rid of all this. So this looks scary, but it's actually pretty easy to do. So all you have to remember is that this N is going to be bonded to these 2 hydrogens. This carbon is going to be bonded to this hydrogen. This carbon is only going to be bonded to this carbon and this carbon. And then these 2 hydrogens are only going to be bonded to this carbon. So we can go ahead and, so we know that hydrogen can only bond once, so it cannot be in the center of the atom. So we have our nitrogen, we have 1 carbon, we have a 2nd carbon, and we have a 3rd carbon. So we do need to sketch out the entire molecule because it does have us trying to find out the number of sigma and pi bonds. So we can go ahead and add our hydrogens. So we have 1 hydrogen here. You don't actually have to draw out the hydrogen and the bonds. You can just draw a bond just going to nowhere because I think it's assumed to be a hydrogen, but I like to draw it because I'm probably going to forget and wonder what I was putting there. This is pretty sloppy, but it's just paint. I don't think, it's not actually showing my webcam, so I don't know if it shows my webcam on the recording, so I'm just going to assume it doesn't. So there we go. So this is our molecule. This is not complete though. This is just the bare bones. We need to find out how many bonds there are. So I pull up Excel, but Excel's throwing up. So now I'm trying to access my, oh, we have someone else. Hello, Jose. I'm trying to access my, should I stop the share? I don't want to, but I want to show my video. How do I manage that? This is not what is this? I hate Zoom, whatever. It doesn't matter. I'll just throw in here. So I'll just say it out loud. I already did these numbers, but I haven't answered in there. So I can go ahead and check just to be sure. After this, I do want to explain it first before I do the answer. So N is going to be 42. That's the number of electrons needed. And that's 4 times 8. So we have these 4 atoms that require 8 electrons, these 4. They require 8. So 4 times 8 is 32. And then we add on to that, each of the hydrogen needs 2. 5 times 10. 10 plus 32 is 42. That's our N number. Our A number will be 22 because hydrogen it has 5 electrons in its valence shell before anything as a neutral atom. and that 5 is added onto the 5 hydrogen electrons. They each have 1, so that's 10. And then we add that 10 to the 3 carbon atoms. Each of them has 4. 3 times 4 is 12, and we add the 12 to the 10, we get 22. So our A is 22. I would draw it here, but I cannot draw numbers with it in. You know, let's pull up we can pull up a notepad. I don't think that will crash my computer. Yeah, this should work. Okay, there we go. 42. That's much better. I don't like just spitting out numbers that I know it's just gonna be forgotten. Okay, so the S is what's really important. We do want our unshared electron number. That is useful, but in this one we specifically want to know how many bonds are going on. So shared is going to be N minus A is 20, which means that we have 10 bonds. And we also have a single unshared electron pair. Just say pair, yeah, P for pair, there we go. So knowing this, we can then go in here and we can see how many bonds we currently have. So we have 1, 2, 3, 4, 5, 6, 7, 8. That means that we are missing 2 bonds. So where do we put these? Now, realistically, nitrogen likes to, this is not really the correct way to do it, but nitrogen likes to make double bonds. So I'm just going to go ahead and assume that's going to be one. But as we can see later, it doesn't really matter whether you assume or not, because this is the only way you can do it. So we go ahead and put these 2 here. And as we can see, this is the only way we can actually put 2 more bonds into this atom, or this molecule, sorry, because if I were to put one right here, this carbon would now be filled. Actually, could we put another one here? I think we might. So I think it's possible to put one here, but nitrogen, I think, wants to have, I think this is the proper way to do it. It could be that the second bond is on here, but for this problem, we just want to know the number of sigma and pi. So whether this second bond is here or if it's here doesn't actually matter. It's kind of just semantics. So, but I would assume it'd go on nitrogen because nitrogen tends to double bond more. But anyway, so the final bond would go on this carbon. The final unpaired bond would actually go on this carbon because it only has 3 bonds. Okay, so we've now finished our molecular structure, and now we're going to count out how many sigma and pi bonds there are. So we have 1, 2, 3, 4, 5, 6, 7, 8. That's 8. Here, sigma. I don't know how to put this symbol, so we'll just do the 8. And then we could count the 2, or we could just, see that there's 10 bonds. So sigma and pi, and there's 2 of those. So we can go ahead and get our answer, 8 sigma and 2 pi bonds, which is 4. We'll go ahead and put that in just to check. And there we go. That was pretty easy. So we can go on, and I don't want to go over every single one of these, which are the following compounds. So this one, the trick to this one, I'll explain it real quick, but I'm not actually going to tell you the answer, but you can probably figure it out. So these fluorines, when you do the fluorine, it's only going to have 1 bond to carbon. So you think, oh, that's just the s orbital, but it's not, because you have the 3 unpaired electrons around it. So it's actually, these fluorines are actually sp3 hybridized. So it immediately makes it so that this wouldn't work, but also it's 1s. So you have to remember, fluorine isn't gonna, its valence shell is, I think it is in energy level 2. So it actually can't do this. No, these fluorines, if it only has carbon and fluorine, it can't do it because it needs a hydrogen or a helium. Now, none of these are heliums, obviously, but it has to have hydrogen for it to work for this problem because it needs a 1s. And not only is not 1s, but also hybridized sp3. So these 2 just wouldn't work. So it has to be this one or these 2 because they have hydrogens and carbons. So I'm not going to tell you which one it is, but I think you can figure it out. So what you have to do is you have to find one of these carbons that has either 4 bonds and or 4 electron pairs, free electron pairs, so that it hybridizes sp3. If it hybridizes sp3d or sp2, aka it has a pi bond, it won't work for this problem. You have to find one of these that does not have a double bond. The carbon has to bond, excuse me, to a hydrogen, and the carbon sp3 hybridized. Now, which one of these it is, I'll leave you to figure that out. But this one's pretty easy. It's pretty easy to understand. You just have to read the instructions really carefully. They'll get you. If you don't realize this has to be 1, it has to be S hybridized, and the atom that bonds to has to be sp3. I might be going into it like a little bit too hard, but that's all right. What atomic orbitals were used to form pi bond? This one doesn't look too hard. I think I can figure it out. This one is just this one's just drawing out the molecule and then figuring out what the hybridization is. It's not too difficult. Add lone pair structure for the answer to the question. Form the pi bond between the oxygen atom and the carbon atom. If you have any questions, Jose, feel free to ask. I'm just going over how to do some of these. What orbitals were used?
Hey, bro, I got a question.
Yeah, go ahead.
I'm still kind of confused, like how to like hybridize, like the whole like process.
How to
and, like,
hybridize?
Yeah, like
so you don't understand like how to find what to turn into hybridization, is what you're saying?
I mean, I kind of get it, but like yeah, like fully like don't fully understand it. Does that make sense?
That's fine. I'll explain it real quick. That's actually pretty that's a pretty good thing to explain. Let's just say new, save. So it's really simple. Okay, it's probably just hard to understand, and like the teacher is trying to get you to understand in a way that has you both understanding the theory as well as like how to actually do the problems. But the really simple way is that, let's say we have, so easiest way to do it, we have this carbon atom, right? And let's say it's like in the first problem where we have CH2. So we have these 2 carbons and they're both connected to a hydrogen. What is CH2 again? Is it like this? Oh, right, had a triple bond. Okay, so what would the hybridization of this be, right? Can you tell? Okay.
Yeah, give me a second. I mean, I wrote some notes.
So talk to me, like what makes you think which hybridization this would be?
I mean, I see like there's like 2 sigmas, 3 sigmas, and then
There's 3 sigmas, yeah. There's 2 pi bonds. So which bond causes an atom to be hybridized? Like which ones need to be hybridized? The sigma or the pi?
The pi, no?
No, not the pi, the sigma. So the pi bonds, if you can remember that pi bonds are p. So here, when you do pi bonds, you're only using the p orbital. So let's see if we can find one that shows what I'm talking about. Okay, so see, when you're doing the pi bonds, it's not actually, the s orbital never does pi bonds. It's actually the p orbitals. So you might want to go look back at our notes, like rewatch some of them, because she explains it better. But basically, you have the p orbitals like this, and when you have a double bond that causes to have a pi bond like this, or 2 of them, the p orbitals, the second and third ones, the first one usually hybridizes with the sp, but the second and third p orbital like shape, like the peanut, is actually in just the p orbital by itself, not hybridized at all, shares electrons across with the other p orbital. So I don't remember the shapes, and they probably don't matter, but these two bonds are actually like, it's like this. I can't draw for crap on paint, but it's like that, except more peanut shaped. It's more like this. Imagine it's like this. And they are bonded with the P's on this carbon. Some funny years. So this one right here, this and this, is bonding with this and this, and the electrons are shared between them, right? And it's the same with this. So because these p orbitals are doing the bonding here, this is a terrible picture, but because these p orbitals are doing the bonding, they're not it doesn't hybridize. So whenever you have, so basically if you have electron pairs, so if these were so if this was a double bond, so it doesn't really matter, but if these had electron pairs right here, those electron pairs also hybridize. So electron pairs and sigma bonds hybridize, right? These both hybridize. You have to put together the s and p orbital in order to get the proper bonds to get enough, basically to get enough bonding space for the new electron. I say new electrons, but the other electrons to fit in. You really should be, you should probably rewatch, like, or ask the things tomorrow. But essentially, whenever you're doing hybridization, you just say, like, just kind of say sp3 and then take away any double bonds you see because they don't hybridize. And then if you have something where carbon is like, it wouldn't be carbon, I don't think. What atom is it? Xe here, let me see. I think it's XEP, XE, it'd be F, yeah. 5? Yeah. So xenon and certain other atoms can actually break the octet rule, and we'll have 10 electron or 5 electron pairs or 10 electrons bonded to them. And in this situation, it would be, instead of being sp3, it would be sp3, and then 3. So each one of these is an electron pair, right? So you have 2 electrons here, and you have 1 electron or 2 electrons, sorry, for each of these p's. So there can only be 2 in s. There can only be 6 in p. So once you have something like this, you actually go into the d sublevel of energy. So then it'd be sp3d hybridized. And so whenever you're figuring these out, you kind of just count up, right? So you have 1 bond here, that's s. That's 2 electrons, it fits into the s. You have a second bond, you have p. Third bond, you have p2. Fourth bond, you have p3. That's what most molecules will get to, or sorry, most atoms will get to in molecules. And then the fifth one, if you have it, will be your d. Now, it can go up from there, but it usually doesn't. It usually only gets to sp3 or sp3d. And it's usually lower than that anyway. And it just, so that's a pretty, if you want something more in depth, something that probably explains it better, so I think on Monday, it'd be on, I think it'd be on Tuesday. Is that when we have our review? I don't remember, but we should have a review, and that'd be a good thing to ask the TAs so they can explain it maybe a little bit better. So we can go over this one. So what orbitals were used to form the sigma bond? So that's the sigma between the oxygen atom and the carbon atom. That is also bond. So it's this one, right? So what it's saying is that, what is the hybridization So if it was asking about a pi bond, right? So this is a sigma. The pi bonds are pure P. So it would just be P. It would be like, it'd be 2P hybridized, I think. Or it wouldn't be hybridized, it'd be 2P. That is it. So see down here, see it says like this, that would be the suborbital energy. It'd just be 2P. But because it's a sigma bond, it has to be hybridized. So this oxygen only has 2 bonds, but it's not sp hybridized because it's oxygen. It wants 8 electrons in its valence shell. So it actually has 2 electron pairs here and here, right? So it would be, this oxygen is sp3. So it has to be sp3. And this carbon, you see that it has a double bond here. So it's actually, so it's not sp3, it's sp2. So as we can see, we have, it'd be number 3. Let's go ahead and throw that in there. Oh wait, this isn't 3, crap. This is, well, there go my points. Oh well, this is a 5. Well, anyway, as you can see, that's right. Yep. So so really all you're doing is subtracting. Oxygen is sp3 until it has a double bond. This carbon is sp3. Oh, it has a double bond. It's sp2. And if it had a triple bond, it would be sp. And if it has two double bonds, that would be sp again because it has 2 sigmas. So you kind of just have to subtract. And then, okay, so in this one, we see we have an sp3d. So that means that we have to find one of them that has a that has 5 bonds, or not 5 bonds, but 4 bonds. And so if it has 4 bonds and it has an unpaired electron pair, this would be sp3d hybridized. So we can go ahead and do this. We can go ahead and do this problem just to show how I find it. That'll help you out. So first of all, this is boron. Let's insert boron real quick. So that one is immediately not going to be it because boron is element number 5. It only wants 6 electrons in its valence shell. So I suppose theoretically it could form an sp3d hybridized, but realistically it's never going to get anything over an sp2. It just isn't. So this boron this is not going to be the right answer immediately. This might be the right answer because it's xenon, it can form that. And like we said, the XeF5 that had sp3d hybridized, but we can't be sure which one it's going to be without doing the problem. So we're just going to pull this up and we're going to, so NaSu. Okay, so SCl4, we don't even need to draw these out, not really. We can just find out how many bonds they have. And if they only have 4 and their unshared isn't enough, or is too many, sorry, then we'll know that we have an sp3d hybridized because the S will have to get that extra unshared electron pair. So we can go ahead and find the N, and that's just 8 times 5. 8 times 5 is 40. And then S, we need a periodic table for this. Let's go. So sulfur is like oxygen, so it's going to have 6. Ooh, that's wrong. We don't need this right now. Save. So sulfur is going to have 6. So 6 plus, 6 plus, and then Cl is 7, I believe. Yeah. So it's in this category. So it's going to have 7 already in its valence shell. So we can add 7 times 3. So that's 21 plus 6. And that's 27. That's odd. Did I do something wrong there? Because oh, right. Okay, I'm dumb. I did something wrong. It's 4, not 3. Because these numbers are very, okay. So another thing to note, if you get an odd number, like 27, you did the math wrong somewhere because the bonds are multiples of 2. So if you see a odd number, you did the math wrong, you have to check it again. So this is 28 plus 6, and that gives us 34. 34. And then 40 minus 34 is 6. And this would be 28. So this is actually something she talks about in class. So this is actually only 3 bonds, right? Because you divide by 2 to find the number of bonds. This is not enough. We actually need 4 bonds. So if in the case like this, where it doesn't have enough bonds, you just ignore the math and just take 2 from here, right? Well, you don't ignore the math. You have to take the electrons out of the unshared. So because you have to have 4 bonds, you just can't not. So as you can see, 8 divided by 2 is 4. We already know that. We want to know how many pairs of electrons there will be. So that would be 13. So each one of these chlorines is going to have 1 bond, and then it's going to have 3 free electron pairs. 3 times 4 is 12. So as we can see, we have a bonus electron pair. The only place the electron pair can go is on the S. So that's going to be sp3d, and these chlorines are going to be sp3. So number 1 is our answer. That was pretty easy, right? Now, this is a homework, so I have no issue getting these wrong once or twice. It's going to be right, but if it weren't, that's fine because I can check it in. But on the test, you want to check all of these. You want to even like you don't. So, but with boron, because it can't do sp3d, it can't. It's just not possible. Like, it's not possible. It's just not possible. Let's just say that it's not possible. So you're just not going to ignore this one. This is clearly the wrong answer. So you just don't check that one. But these other ones, so another thing is that you see this N2O, it's probably going to, I think what it's probably going to do? It's probably going to bond like, let's pull paint back up. It's probably going to bond like this. It's a little sloppy, but so this probably isn't going to sp3 or sp3d hybridize. I mean, it will almost definitely sp3, but it might not sp3d. Or it probably won't, because usually only larger atoms, really big atoms like xenon or sulfur can sp3. Oh, you know what? I forgot. It's sp3d. Okay, so another reason. I completely forgot this. So the D is sublevel 3, right? You have to be this row. You have to be in the 4th energy level for S and P, or the 3rd energy level D, to be able to sp3d hybridize, because this doesn't have this energy level. This row, this is the 3D row right here. If you aren't in this or above, you can't really do it. Wait a minute, but I got S. Oh, you know what? I see why. So the S is it's in the 3rd energy level. I guess this one can as well. I guess the 3rd energy level can, because it's the same energy level as this. I didn't realize it could. That's interesting, actually. I'm not all knowing, unfortunately, so I do not know all. Anyway, so do you feel like you understand it better, or do you want me to maybe go over the notes? Because I can pull up the Jose, I can pull up the notes.
Yeah, I kind of get it now. But okay. Yeah, would you like mind pulling up the notes?
Okay. Yeah, let's see. Let's go to Canvas. I'm gonna stop my share real quick so I can log in my Canvas page. Texas. So I'm not going to do it here, but I'm going to show you principles of chemistry. So if I go into my notebook, where does she explain it? 7. So she explained hybridization in lecture 13. So which lecture are we on right now? We're on lecture 15. So if we go to lectures online, go ahead and share again. Sure. Okay, so see, these are the 15 lectures, right? This is the most recent one, and it goes up, and then this, and oh no, I think it's through my computer's throwing up. Oh no, oh no. I need to close stuff, or it's gonna, my computer's gonna die. Oh no. Oh no, come on, computer, don't do this. Just give it a second. I have opened up too many tabs and my computer is not liking it. That's really unfortunate. Oh my gosh, what is it doing?
It's all good, bro.
Oh my,
I mean,
yeah, this computer.
like, what
This is my older
no.
computer. Okay, no, you can access this. So I'm showing you where it is.
Yeah.
So okay, I
mean,
think I closed enough. But you go to lectures online, and in this
like,
lecture
what
right
date?
here, yeah, this one. This one is lecture 13. In this one, she explains how hybridization works. I just checked my notes. And yeah. So in lecture 13, she goes over, it's not at the beginning of the lecture, it's about halfway through. It looks like she starts going more in depth on how the hybridization works. I think this lecture is mostly explaining the structure, the molecular structure. I think she also explains it at lecture 12. So if you really are having issues with hybridization, these two lectures, you're probably gonna want to rewatch them, because in these two lectures, she explains hybridization as well as molecular shape, which is pretty important for the test that's coming up, I do believe. So if you do find yourself still having problems with these, I would go to that. I'm not a teacher. I'm not a celery teacher, so I'm not the best at explaining them.
Yeah, it's all good. I'll just rewatch those.
Yeah. Are there any other problems you're having issues with? Like any problems on the homework that I can show you how to do? Because that is something I can do.
I mean, as of now, nah, I'm pretty good. It's just that hybridization is giving me like a little trouble.
Okay.
But I'll just like rewatch the lectures.
Yeah.
Just go over it.
I'm probably just gonna do a couple more of these until 4, and then I think I'll probably finish this. I'm going to go over how to do every single one of these, and I'll post a video of it probably on Tuesday. But I don't want to. I just don't want to, post how to do every single one. Like I still did some of them, which I probably shouldn't have done. Oh well.
Yeah, it's all good, man.
Yeah, I just don't want to. I'm just not going to post all of the problems until after it's due. So
yeah, it makes sense.
Yeah. So this is this actually goes over some of this. It goes over bond order, paramagnetic, this sort of thing. So when you do this homework, it should help you understand it a little bit better, I think. But this seems to be going over what we did in the last 1 or 2 lectures a lot more than lectures 12 and 13. This looks like the first 7 problems are going over sigma and pi bonds and hybridization and such. Consider the compound ethylene C2H4 bond. Something bond. Top orbitals that combine to form this bond are. So C2H4. Yeah, it should probably be a double bond, and it says above and below the internuclear axis. So that's almost definitely going to be a pi bond, and then pi bonds are pure p and don't hybridize. So this one should be, it's pretty simple. It's pretty clear that it's going to be one of these two. And, let's open our periodic table back up. Which energy level is carbon in? This one's a hard one. This one's pretty easy. So yeah, some of these are a little bit harder. Ooh, this one looks complicated. The ground state electron configure. Okay, so actually, I think I might want to go over this one. Electron configuration of O2 minus.
Your
This
screen
one looks
just,
complicated. Huh?
I can't see your screen.
You can't see my screen, really.
Yeah.
Let me
Can you see,
restart
like-
the share.
Yeah.
Yeah, my computer throwing up on itself might have messed it up. Can you see my screen now?
Yeah, now I can. Cool.
Okay, I don't know why that was happening. Thanks for telling me.
Yeah.
So I think, do you want me to go over this one? This one looks a little bit scary.
Yeah, that one looks kind of hard.
it probably just looks scary. So this looks like it's going to be a bond order problem. So it's what we were doing in our last lecture, bonding and anti-bonding, that sort of thing. So let's go ahead and I think I'll unshow my screen and I'll show my so O2 minus. Let me find a page to work on. Here's a blank page. Okay, let me just I'll show my notebook because that's the easiest. I can't I don't think I can so you can see me. Hi. So I'm going to draw it out on here. I don't know if my camera is good enough to pick it up. Oh. I might have to do it on paint, but that would really be bad. You know what I'll do? I'll take a picture of an email to myself and then it'll look good. So let me go ahead and do it. So we're doing, this is a bonding anti-bonding problem. So we have our, I haven't done these in for something like a week. So see if I remember how to do this. Oh, it's homework 7. So we have our energy going up. We have sigma bonds, pi bonds. So we have our 2 sigma, and we have our 2 sigma bonds, or not 2 sigma, but that is 2 sigma, I think. Our 2 sigma s bonds or orbitals, or I don't know, this is so weird. I don't really understand this too well myself, bond order stuff. It's a little bit confusing. Atomic orbital electron probability distribution. I understand how to do it. I just don't understand, like, it's the like very much sense to me. Out of phase, in phase. So we have a 2 lower, then we have those 3. Let's move that out of the way. Those 3. And then we have O2 minus, and this is just how many electrons do we have? Is it just like normal where we're doing the okay, so it is just like, so we are just using the valence electrons. So each oxygen has 6 valence electrons. So that's 6 plus 6 is 12. And then we also, so in this one, it's O2 minus actually. So we actually have 13 electrons. So then we're just going to fill up this kind of tree thing. So I'll leave one. This is the thing. This is the number of electrons. I have to draw it out on here because otherwise it's going to be really hard doing. I'll gesture to it and explain it once I take a picture of it once I finish. But draw another one. And then we have those 2. So those are sigma s orbitals, I believe. That does appear to be correct. Yes, sigma 2s, sigma 2s, pi 2p, pi 2p, sigma 2p, and then antibonding and antibonding. So sigma 2s bonding, sigma 2s antibonding. Hello. Sigma 2p bonding, sigma 2p bonding, and then that one is, no, those are pi 2p. Whoops, that's wrong. Yeah, this is hard. I'm gonna have to study this some more before I take the test. We're just going over question 11 right now, and I'm drawing it out on my notebook, and then I'll take a picture of it and show it to you to explain it a little bit better. And then that's sigma 2p, sigma 2p antibonding, pi 2p antibonding, pi 2p antibonding. And then because we have 13 electrons, we're going to fill it up. And then we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I believe that's how it's done. Yes, I do believe that's how it's done. Wait. Do we fill up low to high? I'm not so sure about. Okay, so okay. I see. Okay, so we don't fill that one. Okay, got it. So let me take a picture of this and I'll gesture to it and explain it better. Light. That's pretty good. Okay. And now I have to email this to myself. I can't draw on paint well enough. I'm not going to try to do bond order on paint. That would be pain. So, email. Okay, so now I can reshare. Not to look at me anymore. Okay, here we go. So it's my screen. Actually, I'm gonna stop sharing. Actually, I don't think I want to show you my emails. You're not in your recording this meeting. Okay. Let me just download it real quick. There we go. Got it. Download. Okay, there we go. Downloading. Open it. Now I can share it screen. There we go. Okay, so this is what I just finished doing. Looks really, really good. That's upside down. Here we go. Okay, so this is our molecule. It's our O2 minus. So we're doing this problem right here, right now. Was the ground state electron configuration of O2 minus. So we went ahead. So this is kind of our tree. We have our sigma second energy level S, sigma second energy level S anti-bonding. So this is bonding, anti-bonding. These are bonding, and these are anti-bonding. Then these are pi's. And this is sigma, pi's, sigma, antibonding, and then these are all p. So we fill it up. So the energy level goes up in this direction. I'm sure I can draw on it, but I'm not going to. So the energy level goes up in this direction. So this is higher energy. This is lower energy. And in order to form a bond, it wants to be in the lowest energy state. So you fill it up from the bottom to the top and then level by level. So we fill these two first, and then we fill these three, and then we fill this level. As we see, we ran out, and we get this. We get 1 sigma 2s. We get 1 sigma 2s antibonding. We get 2 pi 2p's bonding, 1 sigma 2p bonding. We get 1 full pi 2p antibonding and 1/2 full pi 2p antibonding. And that should, so as you can see, we just filled it out. This problem does seem to be pretty simple. I don't think it should be too so as you can see, we have so there is our sigma 2s bonding and antibonding. So it looks like we square it. I guess this 2 is for the 2 electrons. That would make sense. And then it's 1, and then these one would be, one of these would be 1. Okay, so we have those two. So this right here, this sigma 2s2 and sigma 2s antibonding 2 is these two right here. And then next up we have sigma 2p2, which would be this one right here. I don't know why that one came first, but that's right. And then we have our pi 2p, and it's going to be 4. It's going to be 4 because we have 4 electrons. And then next we should have 3 pi 2p antibondings. So Okay, it looks like it does it in separate things because it's not complete. Fair enough. So, and then I do believe, yeah, this would be our answer because we have 3 electrons at the end. This one is odd, which is odd, but so it would be number 4. That one was not too scary, I don't think. Just lots of numbers and letters, which are not fun. There we go, we got it right. That one wasn't too hard. It was very scary. I agree. I don't really like the anti-bonding stuff. I don't really understand it very well. So I hope that does explain how to do at least this problem. This seems to be the only one of its type, but that should help you, I guess, do other ones. Did you have any questions, Sameh Akamal?
No, not for this one.
So I just mean for the homework in general. I've already gone over
yeah,
a number of things.
Yeah, I do. For number 5, yeah, I have a
Yeah,
question
number
for that
5?
one, I guess.
Okay. This is number 5 right here. Yep, that's number 5. Okay, what's your question for it?
I thought it was like the sigma bonds would be like between like the carbon and oxygen would be like it would be, since the hybrid, like I guess the regions of high electron density around the carbon that's attached to the sulfur would be like the wait, I thought it was 3 at first, so it would, that which would be
3?
SP. Yeah.
So I got 3, but I think you might have a different problem. So what is your number 3? Like, what is its what's the answer for on your homework sheet? You might want to pull that up real quick because I think we do have like the answers are not in the same place.
All right. Yeah. Oh no, I think they are in the same place. Wait, no, they're not. Never. Yeah, no, never mind. They're not. But my 3 is the same as your 3, though.
But you got the wrong answer.
Yeah.
What is it? What, is your question the same? It might be slightly different.
Yeah. No, it's the same.
Really? Can you take a picture of it and show it to me?
Actually, I was talking about
Which one were you talking about?
No, I was talking about not about like the answer choices, more about like the regions of high electron density, I guess.
So you're asking
carbon.
about how it hybridizes?
Yeah.
Okay, so in this it tells you not to make sure that you put the lone pairs on, but that only really applies to oxygen. So as we can see with carbon, it already has 4 bonds, right? So it doesn't have any lone pairs. So if you remember, every atom that is bonded to it counts as only a single electron density, region of high electron density. So this carbon only has 3 regions, 1, 2, 3. I suppose itself, but we're not talking about it. So having only these 3, its hybridization would be sp2. That's one way to explain why its hybridization is sp2. But also you can tell its hybridization is sp2 because it has a pi bond. And this pi bond is pure, it's a pure 2p connection between C and S, the carbon and the sulfur. So it does not, is not part of the hybridization of carbon. So carbon only hybridizes with 3 electron pairs, forming an sp2 hybridization. Does that answer your question?
Yeah, I got the sp2 for the carbon, but for the oxygen, I thought it was
okay.
sp.
So that's where this comes in. Note that the lone pairs have not been shown in this diagram. So in just looking at this oxygen, it looks like it's an sp hybridization, right? But it's not, because the 2 lone pairs count as regions of electron density. So right here and right here, there's an electron pair. So it's a bit odd, I do agree, that the electron pairs, despite not bonding, count towards hybridization, but they do. They just do. I guess you could look at it as like the regions of electron density, and you have to hybridize that. That works, I guess, because each electron pair is its own region. But however you look at it, it has these 2 bonds right here. They're both sigma, so they both need to be hybridized. And then you have these 2 electron pairs above and below that you have to remember, because oxygen wants 8 electrons in its valence shell. We can go ahead and close this quick. So having a full 8 electrons or 4 pairs of electrons that need to be hybridized, it will hybridize sp3.
Oh yeah.
So it would
Okay,
be
I get it.
sp3 hybridized, not sp. Yeah, you
Oh,
have to remember. Yeah, it was very, so the reason it said this is specifically because this did not have its electron pairs shown, because you do have to use those to hybridize properly.
Okay, I got it.
Yeah, it can be tricky. It is not simple as it might be.
I
So
also
that's the
had a question.
Oh,
Yeah.
what
I
else?
also had a question for number 2.
Number
as well.
2. Okay,
Yeah.
so this one.
Yeah, that one.
Yeah, I went over that one earlier, but I can go ahead and do it again. Sure. Okay,
Thanks.
so let's pull up. We're gonna have to draw. Actually, I already drew it. I don't really want to draw in paint again because it looks truly awful when I draw it in paint. So we're gonna go ahead and take it. I've actually done it on my notebook here, so I can take a picture of it real quick. Here we go. And I'll just send it to myself. There we go. Save. Okay. And now we'll share to my Gmail. And then I'm going to stop sharing for just a second so I can access my email. And if my computer wants to load, download. There we go. It's pretty simple. And we'll go ahead and start the share back up. There we go. Okay, this is, rotate just a second. Okay, so this is so I just want to explain first how to make this atom or this molecule, sorry, because this is a little bit scary, right? This is not immediately obvious how you would turn this string of letters and numbers into a molecule, but it's actually really simple. So basically all you have to understand is that see how this H2 is specifically after the nitrogen,
Right.
so this nitrogen bonds to these 2 hydrogens, right? So
Okay.
as you can see only to the nitrogen, because the hydrogens only bond once. And then after that, we have this carbon and it has a hydrogen after it. So it has a hydrogen on it right there.
Yeah.
This carbon has
Okay.
nothing after it. Before doesn't matter, it's after, because before it's only going to be bonding this carbon and not to nitrogen, but just the carbon. And then after that, we have this carbon. So it has hydrogen after it. So it will have hydrogens bonded to it right there. As you can see, that one in the middle that had no hydrogens after it has no hydrogens bonded to it. So basically, you just have to check and see, okay, we have our nitrogen. That's going to be kind of in the middle of the molecule. Does it have hydrogens on it? Yes, it does. How many? It has 2. So we have 2 bonded to it. Then we check the next one, carbon. Okay, so we put a carbon there. It has a hydrogen bonded to it. So we can see. So you put a hydrogen there. And then this one has none, and this one has 2. So I don't know how well this works for every other molecule, because I'm not like super chemistry buff, but this should work for most number strings like this, where you actually have to figure it out what is the pi and sigma bonds. So then you want to find out how many bonds there are. I can go ahead and do the math real quick in this notepad. So we had N, A, S. You do have to do this, or you won't. It's really hard to figure it out without it. S, U, and then so we can go ahead and do the math real quick. We have 4 8 electron valence shell atoms, so that would be 32. And then we have these 5 atoms that require 2. That's 10. So we have a total of 42 needed. Available, this one has 5. Nitrogen has 5. It's we don't have periodic table. You can just trust me. It has 5 available electrons, and then we have 5 hydrogen atoms. That makes 10. Each of these carbons is has 4, so 4 times 3 is 12. We get 22. And then for shared, we have 20 because it's just n minus a. That's 20. And then we have 2 unshared. So we can go ahead and divide this by 2 to find how many bonded we have. And that's 10. So we have 10 bonds and we have a single pair of unshared electrons. So that's right there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So of course, when you first make it, you're only going to have 8 of these, right? And where do these double bonds go? That doesn't matter too much for this problem because it's actually only asking how many single bonds and how many double bonds you have. But without these there, nitrogen likes to make double and triple bonds. So normally you're going to have it be double and triple bonded, but that's not always true. So I'm not actually sure. I haven't like checked. This double bond could actually go here, I believe, and this unpaired shared pair could go on nitrogen. But for the sake of this problem, it actually doesn't matter. So, this could go here, this could go here. I don't know which one it is, but it's one of them. And then, but it can't, but there will be one here because this one can't have, because it has this hydrogen here. And so the unshared bond, it can only have one of these two have a double bond. So this does have to be here. This is guaranteed, but this I'm not so sure of. Either way, doesn't really matter, right? All we need to know is how many sigma and pi bonds. So we can go at it even without looking at this or this. Well, not looking at this, sorry. Looking at this, we see we have 10 bonds, right? This is only 8 bonds. This is only 8 bonds. This is only 5 bonds. This is 13 bonds. Only 2 of these can be correct anyway, right? It can either be this one or this one because they both have 10 bonds. You can't have less sigma and pi bonds than you have bonds. So only 4 and 1 can be correct. But then when we look at this, we notice we only have 2 double bonds. Double bonds are the only pi bonds that you have. So you have 1, 2 pi bonds. So it has to be this one. But of course, if you count the number of sigma bonds, you'll find we have 1, 2, 3, 4, 5, 6, 7, 8. 8 sigma bonds. Now you do have to be careful and remember that this is not 2 pi's or 2 sigma. This is a sigma and a pi for the double bonds. And if it were a triple bond, which we don't have here, but if it were, it would be 1 sigma and 2 pi bonds. So does that explain your question?
Yeah, it was mainly like how to, I guess, visualize the molecule.
Yeah. So for this, you really have to draw it. You have to like get a piece of paper, go through NASU, find out how many bonds you have, put the hydrogens to each atom, and you just have to figure it out. I mean, I guess you could like, look this up on the internet. It'll probably tell you. So, like, if you just can't figure it out, you can just find that. Oh, this is not the same atom. None of these are the atom we're looking for. So I guess you couldn't find it out if you looked on the internet. That's too bad. This is close. Yeah, it looks like it's not on the internet. Well, that sucks. Oh well, but you get what I'm saying. Like you really do just have to draw it out to figure out specifically what this one is.
Right.
You can try drawing it in paint or just visualizing it, but it's really difficult. You really do need to have like notebook paper. Like during the test, they give you scratch paper, and I would suggest drawing out every molecule that they don't just that they don't give you the structure for like this. And even these, you might want to draw them just to make sure you get the lone pairs properly assigned. So yeah.
Okay, got it. Right. Yeah.
Yeah. If you have any other questions, I'm probably gonna wrap up here.
I was just say I kind of do need help with like number 6 because of
Number 6.
I guess I know that like some atoms I know like xenon and then the
Yeah.
fluorine Like
Yeah.
that, like I guess like violates the octet rule. So is
This
not
one
just-
does not actually. It would have to be XEF5 to immediately violate the octet rule. So yeah. Yeah, with just 4, it doesn't actually violate the octet rule. It requires 5 bonds or 5 bonds and electron pairs to violate the octet rule. And interestingly, it's actually not the xenon. I was thinking it's probably going to be the xenon, but it's not. So what you have to do first, we can go ahead. So for this ish problem, I'm just gonna go through it again. See, this is boron, right? Boron only wants 6 electrons in its valence shell, which would be at best sp2 hybridized. It's probably not going to sp3d hybridize. It almost won't. I don't think it's possible. It might be, but it probably isn't. So we can safely say this isn't going to be it. It just isn't. Additionally, I don't think it can sp3 hybridize because it's not in the third energy shell. Let me just pull up the periodic table real quick. It's not, so as we can see, it's not in the third energy shell like here. So I don't think you can actually put electrons in the D shell anyway. So that already makes it impossible to do this one. These aren't. For one, this is only 3 atoms. So it probably isn't going to, but also they're all in the second shell. So this one's almost definitely not going to either. So the only ones that will are these 3. Now,
okay.
I can see this may be sp3d hybridizing, but it only has 3 oxygens can attach to it. So this one also probably isn't going. We like on the test, I would go through almost all of these anyway, just to be sure. But when we're doing the homework, we can go a little bit faster and say, like, this one's almost definitely not going to hybridize. It's just doesn't have enough atoms to connect to it. So we see these 2, neither of them have 5. So we can't say for sure immediately which one it will be, but we can go through them and we can pull up our notepad and we can do the numbers. So let's go ahead and we can start with SCL. That's not what I want to do. SCL4. We can start with that one and then we can do xenon next. So first we have this, and then for N, it's going to be 5 times 8 because there's 5 atoms and they all want 8 in their octet. So do that. And then for available, S is in the same category as oxygen. So it has 6. And the other, these 4 have 7. 4 times 7 is 28. 28 plus 6 is 34. So we have 34 available. And then for bonds, we have 6. And for unshared, we have 34 minus 6, which is 28. And you'll notice we have 4 atoms that need to be bonded. This is only 3 bonds. We have to steal some electrons or take some electrons from unshared because it has to have enough electrons to bond. So we take those and that gives us 4 bonds. And now we need, so what's important here is actually the number of unshared because it needs to be 1 more than the outer atoms can take so that it will go to the center atom and give us that breaking of the octet rule with 5 electron pairs that will give us the sp3d hybridization. So we can check for, and we'll just say pairs of electrons and we divide that by 2, we get 13. So 12 of those will be taken. So these CLs will have 1 bond connecting it to the center atom, and then it will have 3 pairs of unshared electrons. That's 3 times 4, that's 12. So we have 1 free pair of electrons that can go nowhere except for to the sulfur atom. So it will hybridize sp3d. So 1 is our answer. We can go ahead and check xenon. We can, but it's I'm pretty sure it's not going to. So xenon would be 40 again because it has 5 atoms available. Xenon has 8, and fluorine would be 7 times 4 is 28. What is it? 28 plus 8? That'd be 36, I believe. Yeah, 36. And this would be 4. And wow, that's odd. Yeah, we have to take 4 more from there. 28 now. This would be 8. And that's correct. Yep, that's correct. So that's our 4 bonds. And then we can see this does actually violate the octet rule, but it does not give us sp3d. It's one more. It gives us sp3d2. So this would violate, these both violate the octet rule, but this one is the only one that gives us sp3d. So our answer would actually be 1.
Oh,
So that's interesting. I hadn't done the math on this one yet, but that's interesting. That does violate the octet rule. I wasn't really expecting it, but cool. Anyway, so that answer your question?
yeah.
Or at least
that-
show you how to
yeah,
do
that
it.
helped. Yeah, I didn't really like, I guess, using that like math equation with the, I guess, with the s
The
is equal to
NASU.
n minus a. Yeah.
Do you need some help understanding NASU? Like, do you
Uh,
understand it entirely?
yeah, I think I understand it all the way. Yeah.
No, it's just annoying to use because it takes so long. Yeah, I agree.
Yeah, I guess. I just try to
Yeah.
like, I guess, visualize it sometimes. So
Yeah, basically the n is just, you just multiply however many of these there is, usually by 8. And then with this one, you just have to find like where, like you just have to find the column there on the periodic table. So this one, they have 8 valence, 7, 6, 5, 4, 3, 2, 1. And then these are weird. So we haven't really had to mess with them. I assume that our teacher isn't going to give us those unless she tells us how many valence electrons they have, because otherwise that would be probably a little bit complicated. But I'd assume it'd just be 2 plus however far along it would be there. So that's what A is. You just add those up. Then S is N minus A, and then U is A minus S. And then if S divided by 2 isn't enough bonds, then you have to take some from unshared. And then you just divide these both by 2, and you find out how many bonds you have, and you assign them. And then once you're done with that, you assign all the unshared until everything hits its octet. And then if you have extra, then something has to violate the octet. Usually when you violate the octet, you want to have the biggest atom. So the S, well, not always the biggest. So as we can see, these chlorines, actually they're smaller. I just realized that. But whether they're bigger or not, usually it's the central atom that violates the octet rule. Central or bigger. I guess sulfur is actually bigger because it's because atoms get smaller this way,
right,
and this way, because they haven't gone another energy level or whatever. Anyway, but yeah, I think it just takes a little bit of practice. So yeah, if there's any other questions you have, I can answer them.
yeah, so far, no, I guess that's all pretty much for now.
Okay.
I guess I'm still, yeah, doing the homework, but
Yeah.
because I just noticed it today.
Looks like some of these are actually gonna be a little bit difficult. Oh no. Anyway, well, I kind of need to get back to college, so I'm probably gonna end this here. If you have
Alright.
any questions, feel free to message me. I'll see if I can help you with them. I'm probably going to do another Zoom either tomorrow or before the homework is due tomorrow, because someone said they couldn't hit it, so I'll do another one, I guess. And
Alright.
then I'll do one afterwards where I explain how to do every problem in depth, and I'll post that. It's going to be right before the test, so it's not going to be that useful, but it's whatever. So anyway, I'll see you later. I wish you luck
Yeah.
on tests and homework. Glad
Right,
you
yeah,
showed
you
up.
too.